let's see, let's make this class light. It's Friday, we're almost tired of the week. This is Functional Analysis 2019, this is lecture 11. We were talking about weak and weak topologies. Part 3. Do I have bigger chalk here? I don't think so. Some bigger chalk. All right. So, in the previous two classes, we have discussed this concept of constructing a smallest topology that makes a certain set of maps continuous. And in the last class, we were working a little bit with the weak topology. Right? So the setup was E. Let's just put it a Banach space. E star is its dual space. And now, this is the set of E to R, which are linear and continuous. Norm of F. Start again. Sup of F of X. When X in E is less than or equal to 1. This is a Banach space with this norm. And in the strong topology, so we have the strong topology in E. All of these maps are continuous. But this is not the smallest topology for which all of these maps are continuous. This is called the weak topology. So we consider E with this topology, which we call sigma of E to E star. Right, so this is the topology on E generated by the maps in E star. So this is the smallest topology for which the maps, the functions, the maps F belonging to E star are continuous. Good. We have seen a lot of properties of these, so the notation that we used here to denote weak convergence was, say, xn converges to x, just a little half-sided arrow, or say xn converges to x, say weakly, if you wanted to emphasize weakly. And we have seen that this is okay, so if and only if, say, f of xn converges to f of x for any f in the D. One of the propositions we had last time. And we saw that the weak convergence was if a sequence xn converges to x, then the sequence is bounded and it's lower semi-continuous in the norm. So the norm of x loses to the limit of the norms of xn. And we finished the class, so this is just remarks of the previous class. So we showed that this topology was strictly smaller than the strong topology in the infinite dimensional setting. We exhibited a set, I guess, the sphere, which was closed in the strong topology, but not closed in the weak topology. But this sort of phenomena cannot happen if you are working with convex sets. So one proposition that we saw was that if a set is convex and strongly closed, this means that it is also weakly closed. And of course, if it's convex and weakly closed, it is strongly closed because the closed sets in the weak topology are still closed sets in the strong topology. Okay. So for convex sets being closed, you can be talking either about strong topology or the weak topology. It's the same thing. And we use this fact in the previous class. We finished with a statement of say if xn converges weakly to x, I wanted somehow to extract some sort of convergence in the strong topology. We saw examples that it's not possible to choose a subsequence that converges strongly. This may not happen. But the right setup here is to make use of this property that we proved and start talking about convex combinations of this guy. So, and there exists a sequence of convex combinations of xn that converges strongly to x. Okay, this may be very helpful. I think I'm going to pass for you guys to take a look in the next homework set that you can actually choose this set of convex combinations going to the left. I'm going to go to the right if you want. You're looking to going to the right. So if you start with your sequence x1, x2, x3, x4, x5, blah, blah, blah. All that I'm saying is that it guarantees there is a sequence that is, if the sequence is converging weakly to x, all that I'm saying is that there is a sequence of convex combinations that converges strongly to x. But for some of the applications, for example, if by any chance the sequence of convex combinations always starts, say, this x1 is in the elements of this convex combinations that converges to x with a certain weight that does not disappear. So we have always 1/2 of x1 plus somebody that converges to x. For some applications, it's interesting to have the sequence of convex combinations always starting as big as you want. So you can refine this a little bit and say not only there exists a sequence of convex combinations, let's say yn is a convex combination of, or yk of xn, but also with yk starting at xk. Okay, so you can take a sequence of convex combination that starts at a certain xk. Okay, this is more on the exercise. So let me just maybe, I'll write for you on the board. X is a sequence of convex combinations, let's say yk of xn. So exercise is to show that one can actually choose yk, the element yk belonging to the, say, convex whole of xn, but with n bigger or equal than k. So yk, I will choose that it's a convex combination of elements just starting with k. All right. Now, I want to move the discussion to define a new topology, what we are going to call the weak star topology. Does anyone have any questions on this before we proceed? Is that relatively clear? For those of you who are seeing this for the first time in your life, this takes some time to understand what's going on. Okay, so it's no big deal if you're okay. I'm still floating around a little bit. That is okay. But these are very beautiful concepts, and I strongly suggest that you take a look at the book and read carefully. And again, I emphasize the importance of these things. As you construct a weaker topology, it has fewer open sets, therefore it has more compact sets. So having more compact set is the thing that matters for the applications. Okay, especially when you want to generate some sort of convergence of things. So for the applications in PDEs, it's important to have some mechanism, some sort of compactness mechanism to generate the solutions of the equations and etc. Okay. Let's see. Okay, so now we are going to talk about this so-called weak star topology. I want to talk to you about this. And what is this? Well, recall that your space E, there's your E. Let me actually write it vertically. E. Above E is a space which we call E star. This is the dual of E, maps that act on E. And of course, this is a Banach space. You can talk about the dual of this guy. So this will be the space E star star. Okay. So if you just see this guy as a Banach space, we haven't seen many examples of duals concretely yet, but we will see in the next chapter. For now, it's an abstract concept. So you have, let's say, a Banach space. You have another Banach space, which is the dual of E. And if you see this is a Banach space, the dual of this guy is the third Banach space, E double star. The thing is, so the first observation that I want to make with respect to this chain is that, so just to clarify, so E double star is, again, the set of maps eta from E star to R that are, say, linear and continuous. When I say continuous with respect to the strong topology on E star, on this Banach space. Right. So this space here, it already has here the strong topology. This space here has the strong topology. And it has a weak topology, the topology from E generated by the maps in E star. So this guy has two topologies in here. This Banach space, already, again, it has two topologies. It has the strong topology. We have defined the norm defines a distance, this defines a topology. Here, there is the weak topology of this guy, which is the topology in this set, generated by the maps in the dual set. Okay. And right here, on this guy, we are going to construct a third topology. Okay, this is the strong topology here. This is the weak topology here. We're going to construct the weak star topology here. Okay, so this new topology that we're going to create is just going to exist on spaces which are dual of somebody. Okay. Now what it is? So I want to exploit this fact. So this is just a definition. And I want to exploit the fact, the idea here is to exploit the fact that there is a copy, there is a perfect copy of E inside E double star. Okay? And I'm going to actually show you what this copy is. It's actually very simple. I'm going to construct a map, which I'm going to call, over this coming week, map J. Okay? J is going to be a map from E to E double star. Okay? I'm going to take an element X in E, and I'm going to send this X to some Jx. Jx is a guy in E double star. So I have to tell you what this is. So this is a functional on E star. So I have to tell you how Jx acts on the function f here. So here usually the elements are called x. Here usually I'm calling the elements f, functionals. And here I'm calling, say, etas. Functionals on functionals. Okay? You can go up as many times as you want, right? So I'm trying to send an element x here to an element here, upstairs, jx, and I have to tell you what jx does to a function f. And this is as simple as it could be. So by definition, this will be f of x. Okay? All right, so this actually sends me every x here in E into a map jx that lives right here. And this is actually not only injective, okay? This is not only injective. How would you see that this is injective clearly? So if I took, so this is clearly linear, right? Yeah. If I just take x plus y, and I'm going to send jx plus y, it's going to take every function of f of x. So, I'm sorry. So first we have to see that this jx lies here. So by definition, jx acting in f is this. So jx is a linear guy. It is a bounded. Okay, so several things to see. So first, this obviously jx belongs actually here, right? By definition. So it's clear that jf of f plus g is jx of f plus jx of g, essentially by definition, because these are f plus g acting in x. And this is also bounded, right? So jx acting in f is just, say, f of x that loses to this guy. Okay? So, you mean this function of eta acting on f loses to a certain number times the norm of f. So this is a bounded linear function on E star, hence continuous. So that is okay. I'm actually mapping here into this guy. This jx is actually an element here. That is okay. First is that this map J itself is linear. J itself is linear. If I send lambda x here, this will send to lambda jx here. And if I send x plus y, this will be sent to the element jx plus jy. It is injective. It is injective.
Using Carneiro, because there is a functional side. If a point is non-zero, we can find the functional. When evaluate at this point, we get the square of the norm.
So exactly. So this is injective by Harmonic. Right? But it's more than injective. This is actually an isometry. So this is actually an isometry on its image. It preserves the norm. Right? Because what is the norm of Jx? The norm of Jx in E double star in the target space, right? The norm of this Jx in the E double star is just the, by definition of the norm, is the supremum of this Jx acting on the elements F, where F has norm here E star 1. Or less than or equal to 1 if you want. Okay? But this, by definition, is Jx on acting on a function of f is just f of x. So the sup of f of x over all functionals f with norm less than or equal to 1, we have seen by the duality statement that this is equal to the norm of X. Okay? Again, this is the definition of the norm in this space. This is the definition of the map Jx, and this is the duality statement that we proved.
Model is the answer.
You can put modular, you can do model, yes, or you can do without. That's up to you, right? So we're always mapping in the real numbers. So if you just change f by minus f, the supremum of the modules will be the supremum of the things without the modules. Okay? But if you want, no problem. So what I'm claiming, so then what we have seen is that the norm of x in E is preserved when I send the norm of Jx in E double star. So this is actually an isometric. Another way to show that it's injective. Okay? So this is a linear, injective, isometric map. So it's essentially an isometric bijection to its image. Okay? Now, the nice question here is if it's surjective or not. Okay? So the question and the nice thing to look forward to, or not, depends on the situation, is if J of E is actually equal to double star. I know that it's contained, and I know that it's isometric to its image. Okay? But I don't know if it's the whole thing, or if there are guys which are not of this form. In principle, there may be, right? Okay. Let me not erase my little thing here. So let me, yeah. So the definition here. So if yes, if this J of E is equal to E double star, we call this space E to be a reflexive space. Okay. So you may have heard this word. We will be talking more about reflexive spaces in the next class, but just to mention to you what it is right now, because we have the position to mention it, is just a space where this map is actually surjective. So this is a space which we call reflexive space. As we will see, there are a lot of many nice properties about reflexive spaces. LP for P between 1 and infinity is reflexive. All Hilbert spaces are reflexive. We'll see. Now, unfortunately, this is not always the case. Well, generally, you might have that this is just contained but not equal. Okay? So what we will do is, so generally, this J of E is just contained and it's different from E double star. Meaning that here in E double stars, there are more maps than the ones that are coming from E. Okay? So, the strong topology was a topology generated by the norm in this space. The weak topology in this space was the smallest topology that made all of these maps continuous. Okay? But now you have here some sub-collection of maps. So it's just natural to define what we're going to call the weak star topology as the smallest topology that makes this smallest collection of maps continuous. Okay? So this is even a smaller topology than this one. But instead of making all the maps continuous, I'm just making the sub-collection of maps continuous. So this is referred to the topology on E star generated by the maps on E double star coming from E. Okay? So let's not make a confusion here. So this is the topology of E star generated by the maps coming from E, generated by these maps JX. Okay, so the weak star topology is the smallest topology on E star that makes all the maps JX, X and E. Obviously this is contained in this double star. Continuous. Okay. This is the definition.
So, weaker than weak topology.
It's weaker than the weak topology. So if you want to just say that the open sets in this topology are contained in the open sets of this topology, the open sets of this topology is contained in the open sets of this topology. Okay. Good. Now let's just refresh our memory and play the same game that we did before. Let's just talk a little bit about the open sets of these guys. So let's just talk a little bit. So who would be the open sets? Well, open sets would be some basic open sets. So if I want to make these maps, remember, JX is a map that goes from E star to R. JX is a map that lies here. Alright, so this implies that all of this JX to the minus 1 of V, where V, these are open, they should be open if V contained in R is open. So if I just take one of these functions that I want to make continuous by this topology, this means that the pre-image of open sets here have to be open here. So pre-image of any open set V has to be open here. In particular, pre-images of intervals have to be open here. So these are the sets. This is just a definition. These are the sets that need to be open. Pre-images of open set by all of these functions. And then I have a bunch of sets that need to be open, and I do that construction. Okay, so what's the smallest topology that makes all of these sets open? Finite intersections and then arbitrary unions. Okay, so then you have, so the topology, sigma on E star given by the maps. E is just the finite intersection of this JXI of sets VI minus 1 and then arbitrary unions. Okay, this is just a description of the topology. Again, I can take just these VIs to be intervals, and again I have a basis of open sets. This topology, if I want, I can just take sets. Now it's a little bit of a duality statement what we have before. So we can take just here the xi's are playing the role of fi's before. So we can take say f0 and then x1, x2, xk, and we can take epsilon and construct a neighborhood, say v or say w of say around f0 given by these maps x1, xk, epsilon as being just the functions f that belong to E star such that f minus f0 acting in all of these xi's as the epsilon for I1, 2 up to k. In other words, this is just the intersection from y1 to k of j of xi minus 1 of the interval if you want to say jxi of f0 minus epsilon jxi of f0 plus epsilon. Remember, jx of f is simply f of x. So these are basic sets of this form, jxi minus 1. Right, so function f is in this interval if just jxi of f falls in this guy, minus jxi of f0 is less than epsilon. Jxi of f minus jxi of f0 is just by linearity j of xi of f minus f0, which is just f minus f0 acting on xi. Remember, I'm using this bracket. Bracket means the same thing as f minus f0 acting on xi. Okay. Sometimes I'm shifting between the bracket notation and the parenthesis notation. Whatever is more convenient. So this is a basis of open sets in the sense that every open set in this guy, every open set in this topology would be an arbitrary union of such a finite intersection. So there would have to be some finite intersection of this sort. For some open sets here, these guys you can always make intervals around a certain point. Okay, so you can always, for every open set in the topology and every fixed point f0, there will be a neighborhood of this sort inside that open set that you chose. Okay. So you see that this formulation may be convenient for some proofs where you have, okay, let's get a neighborhood of f0 in the weak star topology. Without loss of generality, we may assume it's like this, and then conclude the proof. Is this clear? Okay? Take a moment to reflect on this. This is exactly what we have done before, just changing the rules of xi's in f0. So as a matter of fact, everything that we're going to do now is just changing the rules of what the x were with the f's before. And that's why this maybe pairing notation is more convenient. It's just the same. Okay. Now, once we have this at hand, let's say, let me just enunciate for you. So the notation here would be, usually I say that a sequence of functions fn converges weak star to f. Okay, so you can put the weak and star, or if you want to emphasize, you can put, say, weak star to f. Okay. Or you can just write fn converges to f, weak star. Whatever you prefer. If you want to write every time that you set topology, that's okay. Good. Good. Let's keep this in mind. Let me write here a proposition. Let me write for you here. So, proposition. What do I want right here? Which is exactly the same as before. So, number one, Fn converges weak star to F if and only if Fn of x converges to f of x for all x in E. 2. If Fn converges weakly to F, converges weakly. So in converges weakly, this implies that Fn converges to F weak star. Just emphasizing. So the weak star topology is weaker than the weak topology. 3. If Fn converges to F weak star, then Fn is bounded, and we have some sort of lower semi-continuity. Star is less than lim inf. Good. Number 4, if Fn converges weak star to F and Xn converges strongly to X, so this last one is strongly, then Fn of Xn converges strongly to F of X. Okay, so it is pretty much in alignment with what we had before. Okay.
This last convergence is also strongly, or?
Yeah, this is just a convergence of real numbers.
Sorry.
This is the only convergence we care when we talk about real numbers. Before we prove this, let me note for you that this topology sigma on E star with the maps from E is also a Hausdorff topology. It's also a Hausdorff topology. Right? In fact, if F1 and F2 are two distinct functions in E star, you don't even have to invoke Rambanach or anything for this. It's just for the definition. If you have two distinct functionals in E star, then there must be a point where they are different. Then there exists an x0 such that F1 of x0 is different than F2 of x0. Right? Otherwise, they would be equal. So if there are two different guys, then we can say that, let's say without loss of generality, that this is less than this. We can just put an alpha in between. Then F1 will belong to this neighborhood here, the jx0 minus 1 of the interval minus infinity alpha. And F2 will belong to this neighborhood jx0 inverse of the neighborhood alpha infinity. These are two open sets which are disjoint. So every two guys, for every two different points, you can place small neighborhoods around each one of them that are disjoint. So this is a Hausdorff topology. And this is just, don't even have to invoke Rambanach here. Good. The proof of this proposition is pretty much proof of the proposition. I'll leave for you guys to do as an exercise. It's pretty much the same that we did before, right? I call your attention for this first fact. So if you don't, you cannot see geometrically a little bit what is this weak star topology. No problem. So if you want to prove that Fn converges to F weak star, it's just take any point in E and apply this Fn in x, this has to converge as a real number to this f of x. Right? Because essentially this guy is jx of Fn, and this guy is jx of f. Okay? So one side is just by definition, this guy converges weakly to f if these maps jx are continuous, so this will have to converge to this guy. And the other side, suppose this holds for all x. Now let's prove this converges weak star to f. Take a neighborhood of f, any neighborhood of this guy, and let's prove that all but finitely many of these Fn fall in this neighborhood. So a neighborhood of f without loss of generality can be taken of the form that was here, just with a finite number of xi's. Now you just take the finite number of xi's, since this converges to f. There will be just finitely many n's for which this is outside the proper neighborhood. And then you just take a big N and you're done. Good. The second one is essentially, there's nothing to be proved here. This is just a definition of the weak star topology, which is a smaller topology than the weak topology. So if it converges strongly, it converges weakly, and it converges weak star. Okay, so this is trivial, essentially 2 is trivial. 3 is nice. This is the dual application of the Banach-Steinhaus theorem. So if this converges weakly star to f, then the sequence is bounded. Maybe we can do 3. So if this converges weakly to f, by the first one, Fn of x converges to f of x for each x in E. In particular, for each x in E, this set Fn of x is bounded. Now, if for each x in the whole set, this set Fn of x is bounded, this means that by the Banach-Steinhaus here, this set Fn has to be bounded. This is 1. Then now you get this conclusion here about the lower semi-continuity of the norm. What you do is you just take, say, just take this expression here. So Fn of x Fn acting in x, or Fn of x if you prefer. This is less than the norm of Fn times the norm of x. So if you take just norm of x to be less than or equal than 1, say, this would just be this. Now we pass to the limit. Fn of x in the limit goes to f of x, because this is where it goes. And this will be less than or equal than the limit when n goes to infinity of the norm of Fn. Now this holds for any x of norm less than or equal to 1. Then you can take the sup on the left hand side here, and the sup of f of x, where x varies over the ball, is just the norm of f. Okay, then you get that. Yeah. So you fill in the details of this. This last part is interesting. That if you converge weak star, Fn to f, and you take a sequence Fn that converges strongly, then this guy will still converge to that guy. It's essentially, again, a simple add and subtraction trick. Let's see. If you want to evaluate this, this loses to what? Fn of xn minus Fn of x. This is what we want. that in the other application, we introduced this f of xn. Now this is somehow a dual application. We have to introduce fn of x. Because this then loses to let's see if I'm correct, maybe not. Norm of fn times norm of xn minus x plus norm of fn minus, no. Yeah. This goes to 0 by the definition of the weak star topology. Fn converges weakly star to f. This means that this goes to 0 for any fixed x. And this goes to 0 by hypothesis, and this is bounded by the previous item. So you really get this. Right. Now it's a nice exercise to try to play with these things and say, okay, so let me see if I weaken a little bit more, say this condition here, do I still get the result? And the answer is, for this particular case, is no. And you can play, and it's very enlightening if you want to learn the subject, to try to generate counterexamples, try to see if the statements hold if you change this by a very a stronger condition or even a weaker condition. So for example, if you try to weaken this a little bit, so if you just assume xn converging weakly to x and not strongly, and you assume this, or even if you assume more, let's say that fn converges weakly to f and xn converges weakly to x, the question is, do we have a star? Do we have these things? So for example, question. If this is true, do we still have the fn? And for example, the answer for this, I guess, is no. And
xn converges weakly to x, or?
yeah. So if fn converges weakly to f and if xn converges weakly to x, I'm trying to weaken this a little bit. So we have proved that xn converges to x strongly. I want to see if something like this holds if xn converges to x just weakly. And I'm saying that no, then you cannot conclude this anymore. So the first example you have to come up with is these little L2 things. This is usually the most basic example. So if you just take fn to be a bunch of zeros and 1 in the position n, and the same for xn's, and the pairing is just the multiplication coordinate to coordinate. So both of these sequences we have seen converge weakly to 0. Right, so it's converges weakly to 0, 0. But the pairing fn acting on xn, how much it is? 1 for each n, so it cannot converge to 0. Okay, so this is a counterexample for these things. Play with this a little bit in the exercises of the book. There are several of these nice examples. All right, so far, so good? So keep these details in mind. So this weak star topology is a third topology that you put, but you only put it in the dual space E star. Okay.
This is in L2 or?
This is in little L2. Little L2
is reflexive, so it's 2 or not?
Little L2 is a reflexive space.
Yeah.
So this is not true.
Why? Because if, for example, if the space is reflexive, so in this case, GA is same with the E double star. Right? So
Yes.
maybe xn and x.
But I'm putting constructing converging weakly here. So I'm weakening. Was strong. If this is a strong convergence in here, then it's okay. But if you just replace by weak, then it's not okay to have this convergence anymore. I mean, it just may not happen. Okay. Right. So as I was saying, this is a third topology that we put in the dual space, and one of the nicest theorems, and perhaps we should discuss this now, is this theorem of Banach-Alaoglu. Which says that the unit ball B, unit ball on the dual space, so this is just F in the dual space, such that norm of F is less than or equal to 1, is compact in the weak star topology. Okay. So another one for your toolbox. First, if you are in infinite dimensions, the unit ball is never compact in the strong topology, right? We know that. We won't be saying this out loud if we don't know. And this is a nice one. So one of the nice reasons that we have been constructing these weak topologies is to get some sort of theorem like this. This is good. So we have somehow generated some sort of compactness out of these weak topologies. Finally. Right? So the unit ball on the dual space, this is where this topology exists, right? So the unit ball in this dual space is compact in the weak star topology. All right? So we will see in a little bit when the space is reflexive. When the space is reflexive, then this map will be the full thing and so on. Some of these compactness statements can be transferred to the weak topology here and here. Okay, so this is the importance of, working here just with a dual space in the weak star topology, but the way this comes out into play, generally speaking, for applications is when you're working with reflexive spaces. But today let's focus the end of the class today maybe for this, and then next week we're going to start talking about reflexive spaces. So this is a very nice statement. Let's see if we can. Now, before proving this thing, let me do a digression here with you guys and discuss a little bit of general topology. So this is just some facts of life here. If you have, say, an infinite collection of topological spaces, so if you have, say, E alpha with topologies T alpha, so this is topological spaces here, E alpha with topology T alpha. This is an infinite collection, or countable, uncountable, whatever you want. Some sort of collection of topological spaces. Right? You may try to do the product space of these guys. Same thing as you have R, so you know the open sets of R, and you want to construct on R2. If I give you R cross R, and I ask you who the open sets in R2 should be. And you say essentially, well, I mean, if I have two copies of R, if I have R across R, and I make it R2, who my open set should be, and you say, well, maybe one first approximation would be I take the open sets with this guy, cross the open sets of the other guy. This certainly should be open in R2, and then I will construct the smallest topology such that these guys are open in R2, and this will essentially be the topology of R2. This will be the topology of R2, right? So if I take this just a little interval here with a little interval here and make a little square, little open square, of course the topology in R2 is generated by little open squares. This is a basis of the topology in R2. So in some sense, maybe you have not thought it this way, but if you know the topology of R, if you know who the open sets are, and then you take two copies of R, so the most trivial thing to define a topology in this product space is to get an open set here, cross an open set here, and declare that, okay, a product of open sets will be an open set in the product space, and then construct the smallest topology in the product space that contains those sort of sets. And this is essentially what this does. Right? Now, if you have a finite number of spaces, that's okay. If you have a countable number of spaces, well, still okay, it gets a bit trickier, but if you have an infinite number of spaces, well, it's as hard as if you have a countable number of spaces, but let's see. So what I want is to construct this product space X, just to be the product spaces of E alpha, the topology E alpha, product over alpha. And I want to define the topology in X. So the definition of the product topology, if you want, so if nobody says anything on the contrary to you, so if they work with a product space, they are usually working, if nothing is said, they're working with the product topology. Okay, so if you do a product of topological spaces, the product topology is just the smallest topology that makes all the projections continuous. This is just the smallest topology that makes the projections, and if you want to say projections, say P alpha from X to E alpha, projections in the coordinate alpha, continuous. Oh, okay, so now I have been giving the ball to you, now you can play this game. So it's the smallest topology that makes a certain set of maps continuous. You say, okay, Emmanuel, there should be enough for me to go on. And then this is exactly as we defined before. So if you take an open set here, the pre-image, well, but the projection, the pre-image of this guy will just be, say, this guy in the coordinate alpha, and all the rest will be just the entire space. So if you look the projection of a set V here, if you lift, this will just be V in the position alpha, and all the rest will be just the E alphas here. Well, I cannot even count, right? But this is an uncountable graph. So this is just a projection of, this is just the point in here, where in this coordinate alpha 0, you have a certain set, and all in the other coordinates you have the whole space. If you took, okay, so this, by definition, should be an open set. And this is all. These are all the sets that need to be open, if this is the smallest topology that makes this projection continuous, right? And now you take the game. You take finite intersections of these guys and arbitrary union. But when you take finite intersections, so if you take finite intersections, so if this has an open set V in one coordinate and the whole space in the other coordinate, and then you take an intersection of somebody that has the space here, E alpha 0, and a set W in the other coordinate, you would get V, you would get W, and you would get the rest of the E alphas. Okay? So finite intersections, at the end, what you discover is that, and remember, every time that we did this process, this was in the first class of this week, right? So if you have a finite collection of open sets, you do the finite intersections and then arbitrary unions. But these finite intersections, they are a basis for the topology. So in fact, the basis of this topology, are the open sets In other words, this is the topology generated by the open sets of the form, let's say, product. There's the product in alpha of V alpha, where V alpha contained in alpha is open, and V alpha is different from E alpha for finitely many alphas. Okay, these are the basic open sets. It's the product of open sets in some coordinates, but just finite number of coordinates. So in the complement of the coordinates, there will be the full set. So this is the basis of this topology. Okay. Good. Okay. We're gonna need this to discuss this the Banach-Logo theory. Good. So the idea let's try to write on the proof of the. Before we go to the proof, we will invoke this theorem. Let me spell it right. Tikhonov. See if I don't misspell it. Well, at least this is how it's spelled in the book. We will use this theorem of Tikhonov that the product of compact spaces is compact in the product topology. Okay, so if K alphas are compact topological spaces, then product in alpha of K alpha is compact. Infinite product. So it's, I want to leave as an exercise for you to take a look at the proof of this theorem. This is the deep theorem, so go in the book, take a look at the proof, and learn how to prove this theorem.
If you prove for finite is enough?
No, not for the application that we have here. Because we're going to use this thing. So this is an exercise in the following homework set, okay? So as I told you, the homework sets, they complement the classes, okay? So all the theorems that I think you should know, or you should know how to prove at least once in your life, either we'll do it here, or you do it in the homework.
But sometimes statement is enough, I think.
Well,
Because if you look the proof, okay, I understand, but after some days we forget, so
No.
if you remember the statement is very...
absolutely. But you should do the proofs of the theorems that you use at least once in your life. It is okay. I don't think I can do the proof of this right now, if you ask me.
Yeah.
I'm honest with you. Maybe I can try, but I'm not sure I will get it. But you have to do it once in your life. And after that, you have to actually learn the statement and how to use it. That's the most important part. But you really have to do the proofs of the theorems that you use once in your life to, let's say, be worthy of using that theorem. Okay?
The famous proof uses the axiom of choice.
That's okay too. I mean, you can live in a world where the axiom of choice is okay, and so on, that's okay. Well, at least that's just my view, okay? If you don't want to take a look at the proof and learn how to use it, that's okay too. I mean, if you have more important things to do. But if you have time, these are important theorems. You should do the proof at least once in your life. If I'm putting the homework, I would like you to actually take the solutions of this homework, write it very neatly and so on, because one day you will be teaching this class for your students, and you will see the value of what I'm talking about. You will get the same homework that I'm getting, you will put new exercises that you like, and you already have your course prepared for you, you know? This is very nice.
And someone will ask us not to put this in the homework.
Yes. But then you will have the urgency to do to your students what you were forced to do and you didn't like. No, if I suffer this, you will suffer too. Let's see. So what's the deal now? So the idea here, so the idea is to construct, so you have your space E, and the idea is to work on this space X, which is just a product of R, copy of several copies of R, indexed by the elements in E. So this is your original initial topological space. We're going to be working in here. So it's a product of several copies of R indexed by my elements in E. This is okay. R is a topological space with its usual topology. I'm taking a certain infinite product of copies of R. I don't know how many, it's certainly a lot. And I know how to construct the product topology on this space. So this space for me is a product space with a product topology. Okay? Good. Now we're going to take, okay, so now take this set, let's call it C, which is just going to be, again, the product over all X contained in E, but not of all R, but just of the interval, say, minus norm of X plus norm of X of the closed interval. Okay? So this is obviously contained in X, right? And since each of these is compact on R, this is just minus norm minus A to A. Since this is a compact interval on R, a product of compact intervals is going to be compact in this product topology, by this theorem. Okay, so by theorem, C is compact on X. Okay. Now let's see what this has to do with our lives here. So when I take, so you see why I'm choosing this topological space X, because when I take for each X in E a real number, what am I doing?
Choosing a function?
I'm just choosing a function, not even a functional.
Yeah.
I'm just choosing a function. So the elements of X, so essentially X is just the space of all functions, if you want, G from E to R. That's it. It's just space of all functions, G from E to R. Right? The space of linear functionals, the space of functionals, E star, sits here. They are not just any functions. These are functions that are linear and bounded. Okay? So, but it sits in there. So you see that the ball of the unit ball of the dual, right, sits in X. Right, sits in X. The unit ball of the dual is what? Is just the functions f from E to R, which are linear. and continuous. Continuous is equivalent to being bounded, but being bounded and being this unit ball means that which actually means that, well, norm of f will be less than or equal than 1 actually means that f of x is less than or equal than x for all x in B. This is the same this.
Sorry, why bounded means that its modulus is less than 1?
This is the ball. The unit ball on dual is this thing.
Yeah.
It's the functionals that are linear and they are bounded with the bound norm less than or equal than 1, because this is the unit ball by definition. But being bounded with norm less than or equal than 1 by definition is just satisfying this inequality. F of x being less than or equal than more absolute norm of x for all x in the space. So I was going to say that BE sits on x. It obviously is inside x, right? Because these functions are, the functions of this type are obviously functions, right? But it not only sits in x, it sits where? It sits in this C. Because every element is taken into a real number which has absolute value at most the norm of x. So it sits in this interval. So this BE is contained in what I call C, which is contained in x. This is our first observation. Okay? Okay. Good. Now, you see, we are discussing about different topologies, okay? I told you that X has a topology. But I am trying to work with this BE, so the thing here is there are two topologies in play. X has a topology, and this is a subset in X. So this subset has the induced topology. So every time I have a topology in a bigger set, and I consider a small set there, I have what I call the induced topology, which is just the intersections of the open sets here with this set. I baptize these guys to be the open sets in this smaller guy. On the other hand, this guy already comes equipped with the, I'm trying to study this guy with the weak star topology. Okay, so I have to make some sort of link between these two. So on one side I have B of B star with the weak star topology. So I have this one entity, and the other entity I have B of E contained in X with the induced topology. So in principle, these could be two different topological spaces. Okay, but I claim to you that these are the same. That the induced topology that this unit ball gets from this space X is actually the same as the weak star topology. Let's see that. How would we prove this?
It proves that the basis of every topological space is open in the other.
Exactly. So let's prove that the guy in the base of one. So let's take a base of this product space. So what is this thing? So let's see what I want to do.
B star is the smallest topology.
So as just this. So what is a basis of X?
It's the product of copies of X except for finitely many positions. Once they can be
As a base of X. So what is an open set in the basis of X? So this open set. So let me call what is an open set in in open sets like in a basis of the topology. Next, what are the open sets in the product topology there? Are just, so you can take a sets like, so these are functions from E to R. Remember that each projection has to be continuous. So these are just sets of, if you fix G0 and then elements x1, x2, xk, and epsilon, these are just the sets of functions. You can take the neighborhood W, which is a function G from E to R, any function, such that G minus G0, say, acting on xi is less than epsilon for I, 1, 2, 3, k. This is the basis of this topology. Okay, it's just well, pre-images of little intervals on R for finitely made guys. So we have this, you fixed one function, G0, the guys that are in the neighborhood of G0, the guys such that G of xi minus G0 of xi are less than epsilon for some finite numbers.
But this is in
the whole X.
No, we can start topology, right?
No, this is in the product topology. This is the product topology of X, right? I'm asking to you, so remember, fix this G0, fix that G0 in X, right? Fix a function. I'm asking, what's a neighborhood of this guy? What's a neighborhood of this guy? A neighborhood of this guy is the set of G's such that G minus G0 acting some finite number of xi is small. So it's the pre-image of G0 of xi minus epsilon, G0 of xi plus epsilon for some finite number of xi's, just finite number. Okay, so this is what a basic neighborhood is. Pretty much like we did for the weak topology, like we did for the weak star topology. So if you take these sets, any open set in this topology, if you give me any open set at any point G0, I will construct an open set like this that is inside the open set that you gave me. Okay? So these are the open sets that are a basis of topologies of X. So what happens if you take this W and you intersect with the B E star?
And we will require modulus of G to be less than 1.
You would require K. What? You would require not only G to be, you would now require G to be from E to R to be linear, because linear is not something that requires to be linear, to be bounded, and such that this happens. G minus G0 psi less than epsilon. Okay? But then this is just a basic neighborhood, which is for the weak star topology, no? I've seen that the bases were like this. Okay. So what I'm trying to say is that the topology induced by X induces the same basic neighborhoods that you had before. Let's see if we got this right. Let's see if we really understood this issue.
But is every open basis in the weak star topology comes from this process? We also need to prove it.
So let's see. So let's see what we want to show. What I want to show is that, so if you have your space here, BE, B star, and you have, it sits bigger in the space X that has its own topology, right? And you want to take an open set in X and intersect with BE. These are the open sets in the induced topology. So let's first take a construction like this. Let me take an open set here in X, and let me intersect with BE and construct this set. This is an open set in the induced topology. Let me prove to you that it's an open set in the topology that I had here initially. Okay? Okay. So fix a point, say G0 here, BE. So in particular, G0 is already a linear map which has norm at most 1. Okay? Now, since G0 lies inside this big neighborhood here, there is a guy in the basis that is of this shape. There is a round G. Okay? Good. Good. Now, this is what I call W. W intersection BE is exactly this. But now remember that G0 was a linear guy. And this is a neighborhood in the weak star topology, right? This is perhaps a neighborhood in the... So this guy here, just the intersection of this thing here, is an open set in the weak star topology. Okay? Therefore, so what did I do? So I wanted to prove that this whole thing was open in the weak star topology. All I have to do is for every point to show that I have an open set, one of the basic open sets inside. So this is exactly what I did. For fixed G0, I proved there was a basic open set here inside the intersection. Okay? So I showed that the intersection of these guys with these guys are open sets in the topology that I already had here. Conversely, let me show that any open set that we had in this topology here is actually an open set in the whole space intersection of the ball. Let me show that every open set is like this too, so proving that the two topologies are the same. Now if I give you, say, any open set here in this unit ball, okay, if I fix a point, G0, and this guy, I want to show that this is an open set also in the induced topology, in the topology of X.
But we know what is this form of.
But I know that around this open set that you gave me, there is a basic open set of this form. Okay? In which my function has to be linear. Well, but this just sits inside this set where the functions don't have to be linear or continuous. And this is an open set for the big topology. Okay, so this in fact sits a bigger set in the induced topology intersection the unit ball of the linear thing. So you can prove that the open sets that you had here before and the ones that are induced are the exact same open sets by proving that the bases are different. Are we good? So think about this. So think about it and formalize. Okay? But this is the trick. Okay, so once you're this, so you saw how the weak star topology entered here, guys. The weak star topology entered here essentially because it has the same shape of the product topology there of the maps. And now, once you have reached this point, the conclusion is we are very close, right? So you now have B, E star sitting on that compact C that sits on X. So this is with the topology in X, this is with the induced topology in X. And this, you can see this, so I can see everything now inside X. So I can see everything inside X. I can regard all these sets as having the induced topology in X. This is compact. Okay? So all I need to show now is that this set here is closed. Need to show that BE is closed in X. Because whenever I have a closed set inside a compact, this is compact. Right? So all I have to show, this is a closed set. Okay, and it's the final part. And to show that it's closed, I will just write to you this set BE as an intersection of a bunch of closed sets, which is exactly what as the definition suggests. So recall that this set X, all the projection maps are continuous. Okay? So this BE star, we're going to finish in a few minutes. So this is just the sets of F, say from E to R, that verify the following three things. So one, for each fixed X, f of X is less than or equal than value of X. Two, f is linear, so f of, for each x and y, f of x plus y is equal to f of x plus f of y. And three, f of lambda x is equal to lambda of f of x. So if it verifies the three properties, if it's linear, these are these two properties. And if it's bounded by this, then it's a guy here. Okay? So you can just write. This implies that your BE star is just going to be the intersection now how do I want to say this? Of
We can say it is the pre-image.
the pre-image of these guys.
X, and when we say X as a function of.
Okay, so let me write. So the intersection of E of these guys, the guys that f of x belongs to the interval minus x, x, intersection. Yeah, let me just write these things with the functions that are f of x plus y minus f of x minus f of y is 0. Intersection, all x in E and lambda in R, such that f of lambda x minus lambda f of x is 0. Okay? So all of these maps, when I fix an element here and I send to the point x, these are continuous maps. So the set of maps F, the set of maps, so if I fix an E, the set of maps F in this big set X, such that f of x lies in this interval, so this is just the pre-image of this interval in that coordinate x. So it's a pre-image of a closed set. So pre-image of a closed set is a closed set. Okay, so all of these guys, for each fixed x, the set of f that verifies this is a closed set there, so this is a bunch of intersection of closed set. This is closed. Now this one, for each fixed x and y, the map that sends one f right here in the whole space to this f of x plus y is a continuous map. The map that sends to f of x is a continuous map. The map that sends to f of y is a continuous map. Linear combination of continuous maps is continuous map. So the map that sends f to this thing here is continuous. Now I want just the set where this is 0. Okay, so this is the pre-image of a continuous function. The pre-image of this there, this is the pre-image of a closed set. Okay, so where a continuous function is equal to 0. So the pre-image of 0 by this continuous function is closed there. Same here. For every x in E and every lambda in R, the map that sends f to f of lambda x is continuous. The map that sends f to lambda f of x is continuous. So the linear combination is continuous. So you have a map that sends f in E to this guy, and you want it to make equal to 0. This is the pre-image of 0 by this continuous map is closed in X. Okay?
I just have one objection that in the second intersection we define the pre-images of functions of one variable. But here we say we are taking the pre-image under functions of two variables. Because now f of x...
No. The functions are always f from x to r, right? So these are my functions. So, functions belong to x. These are functions from E to R. Okay? What I'm telling you, and this is an important thing so you can understand what's going on here. So you fix x and y. You fix two guys. Okay? These are fixed. So if I want to say, so there is a map here. There's the projection map. There's the projection map. Let's say projection x. That goes from projection little x. That goes from x to r, which just takes me a function f and sends to the point f of x. Okay? This is the projection x. So what I'm telling you is that what I want is to get projection x plus y minus projection x minus projection y. These are three maps of f. Okay? This is a continuous map from x to r. This is a continuous map from x to r. This is a continuous map from x to r. Sum of three maps is a continuous map from x to r. So this is just f of x plus y minus f of x minus f of y. The projection x plus y minus projection x acting in f. Okay? And what you want is that this is equal to 0. So this is just this continuous map, the pre-image of this set 0. This is a continuous map. This is a pre-image of a closed set. So this is closed in here. Okay? And now you're taking a bunch of intersection over all x and y. But for each fixed x and y, this is the pre-image of a closed set. Okay, this is an important question. It's a little bit tricky to think about the fixed x and y. This is actually a continuous map, but this is essentially what it is, right? So this is the intersection of a bunch of closed sets, and we conclude the proof here. This set is actually closed and lives inside a compact because of Tikhonov's theorem, and the induced topology is the same. So a closed set inside a compact is compact with this induced topology, which is the same as the weak star topology. Very nice. Not easy at all, but very, very important. Okay? So, great. We finished this week with this nice result. You keep this result up to mind. You have the weekend to think about the homework that you have at hand, but start taking a look at the book, this section 2. So next week we'll discuss a little bit about reflexive spaces and separable spaces. I still think we're going to keep within chapter 3, and I hope to finish next week before I travel. Good weekend to everyone, and we continue next week.